Welcome to another 2-Bit Da Vinci video, where today we're going to talk about the truth about Tesla's batteries. Thanks to all of you who voted in our last poll, and to anyone who's new, we hope you'll subscribe and take part in our future polls to see what topics we cover next. If you're thinking about a Tesla, you've undoubtedly heard about how cheap they are to fill up, how little maintenance they require, and with recent Model 3 production ramp-ups, we're on the verge of absolute Tesla ubiquity. But one question that we believe keeps potential buyers up at night surrounds their battery packs. So we've compiled a list of all the questions we've received, and we're going to break it down step by step in this 2-part video series. To understand the battery technology, it's important to think about it in these categories. First, we'll look at the raw materials required to create lithium-ion batteries. Second, we'll look at the battery cell manufacturing. In part 2, we'll look at the complete battery pack manufacturing, the final car manufacturing, and the end-of-life recycling of lithium-ion batteries. The first step in this journey has to begin with the acquisition of the raw materials that make EVs possible. We're often told that mining operations for lithium and other battery materials is worse for the environment than just making petrol cars. So is this true? Are we destroying the world by making battery packs for EVs? Let's break this down element by element. Different car makers use different cathode chemistries for lithium-ion batteries. Tesla uses NCA chemistry, or nickel, cobalt, and aluminium. They use this particular chemistry because it offers great energy density, long cycle life, and great charge performance. This makes Tesla's batteries the absolute top of the line in the EV world. They weigh less, last longer, and power the performance of things like ludicrous mode. Most other EV manufacturers have opted to use NMC, or nickel manganese cobalt, which has slightly lower energy density, but is regarded as a safer battery. More on this later. Tesla's batteries have gone through 3 stages. Stage 1 was from 2009 to 2012, found in the Roadster and Model S. Stage 2 was from 2016 to 2018 and powered the Model S Generation 2 and the Model X. Stage 3 starts with the Model 3 in 2018. So what's changed and how are they improving? Stage 1 batteries were constructed with 18650 cells, which were 18mm wide and 65mm tall. They had an NCA formulation that required 11 kilograms of cobalt in the cathode per car. They had a pure graphite anode with no silicon. Stage 2 batteries use the same 18650 cells, but reduced the amount of cobalt required in the cathode from 11 to just 7 kilograms per car. They also introduced a small amount of silicon into their anode. So let's talk about anodes, where common materials include graphite and silicon oxide. Both graphite, a very common stable form of carbon, and silicon live on the same column of the periodic table, giving them 4 valence electrons. This ability to form 4 covalent bonds not only makes carbon the building block of all life on Earth, but also a great anode material. Silicon is very similar, but allows 10 times the energy capacity of graphite. It's clear that silicon anodes are the future, but the problem with silicon is that while graphite expands about 7 to 10% in volume from empty to fully charged, silicon expands between 300 and 400%. This is a big problem, because while pure silicon anodes could use less material, allowing for larger cathodes and thus greater energy density, the repeated expansion and collapse during charge and discharge cycles severely reduces its operating life. So in Tesla's Stage 2 batteries, they use a hybrid graphite silicon anode with between 5 and 15% silicon. Stage 3 batteries are new for Tesla and first shipped with the Model 3. Stage 3 batteries have further reduced the amount of cobalt to just 4.5 kilograms per vehicle. They also have a hybrid silicon graphite anode, and while proprietary and unreported, probably higher silicon content than the Stage 2 batteries. So why is lithium so popular for cathodes? Let's look at the leftmost column of the periodic table. These are the alkali metals, and they have 1 valence electron. So metals here are likely to give up 1 electron, which is very important for the production of electricity, and lithium is the lightest of these metals. It turns out that lithium is the 25th most abundant element on Earth. However, it only makes up 0.0007% of the Earth's crust. Most lithium extraction actually happens in liquid brine pools. Water is evaporated off by the sun, and lithium compounds can be extracted. A majority of current lithium deposits are in the lithium triangle of Bolivia, Chile, and Argentina. Australia and China are also big markets, and their role will only increase in the future. There is also lithium in the oceans, and estimates place it around 230 billion tons, but it's in very low concentrations. Though there is no companies extracting lithium from the world's oceans today, when demand rises or supply dwindles to the point where it's profitable, you can be sure they will. The price for lithium is right around $7.50 US per pound as of 2018. And looking at past prices, you can see lithium has been surging, and the prices in the future will hinge upon supply, as demand is just getting started. Next up is nickel, which has an abundance of 0.009% in the Earth's crust. Nickel is widely viewed as the most important element for EV batteries, and looking at this graph, you can see it's the largest constituent in Tesla's batteries by mass. It plays a pretty big role in battery packs for other manufacturers as well, and will be a key element as worldwide EV shipments continue to rise. Nickel prices are around $4 per pound in 2018, and Canada is Tesla's best bet for a pure North American supply chain. Next, we have cobalt, which comprises 0.003% of the Earth's crust. Now, this is where things get interesting because cobalt is the most critical element in their battery supply chain. Cobalt is the most expensive material here, costing just shy of $40 per pound in 2018. This is due to the scarcity, but also due to the fact that over 60% of the worldwide production comes from the Democratic Republic of Congo. Here, political turmoil, child labor concerns, and violence in this region make cobalt the most critical element in the supply chain. And it is no surprise that Tesla is reducing its reliance on cobalt with each generation of battery. Manganese comprises 0.11% of the Earth's crust, making it the 12th most abundant element. You'll notice there is no manganese in Tesla's batteries, while it is used on most other EVs. This is an interesting move for Tesla considering manganese is so cheap at only 93 cents per pound in 2018. But when you factor a larger requirement for cobalt in NMC batteries, it's less surprising. There's also a small amount of aluminium in the NCA battery, but luckily it is the 7th most abundant element on Earth by mass, and has a very mature supply chain, due to its use in everything from cans, cars, and aircrafts. This makes aluminium very affordable at only 86 cents per pound. And this is no concern at all for Tesla. Now, all those elements are used in the cathode, and the story in the anode is simpler, where there's graphite, which costs roughly 60 cents per pound, and the average Tesla battery pack contains about 54 kilograms of graphite. While only 25% of graphite was used in batteries in 2012, that number is sure to rise substantially. There aren't too many concerns here, especially considering graphite can be created synthetically in the lab, and as demand soars, synthetic graphite labs are sure to pop up. We wanted to talk about raw materials because unlike other companies that are planning to sell tens of thousands of EVs each year, Tesla is planning to sell 500,000 and then 1 million EVs each year. It's absolutely crucial to understand supply chain fragility when considering that lithium-ion battery production is set to soar. The good news is that all these materials have been mined for decades, and most data suggests there won't be any issues with supply limitations for Tesla's goal of 1 million cars a year. But as more manufacturers start believing in the same vision, there's sure to be a strain on some of the critical elements. So be sure to stay up to date with the raw material supply chain news, because it will be absolutely critical in the next 10 years. We aren't going to cover the environmental impact of mining batteries versus petrol cars in this video, but make sure to subscribe for a future video where we will do just that. Now that we've gotten that out of the way, let's talk about the battery cell manufacturing. As you've probably heard, Tesla opened Gigafactory 1 in Sparks, Nevada, and though it will only be fully completed by 2020, it's pumping out batteries and will only increase its production rate as it nears completion. Tesla has switched from 18650 cells to 2170 cells because it is an optimized size for maximum energy with minimal increases in weight and excellent cost. Voltage is largely unchanged since it's a function of battery chemistry. So the big question here is, why does Tesla use these little battery cells when they know they'll need thousands of them? Why not make a big custom battery like the ones found in BMW i3s? The i3 uses prismatic batteries with big custom packs. The Chevy Bolt and Leaf use rectangular pouch batteries, which you might think make more sense because there's less wasted space. But to understand Tesla's choice for cylindrical, small cells, we have to consider commonality versus customization and design flexibility. The i3's prismatic battery and the bolt pouch battery have to be specifically made for those cars. They are built to specification much like your smartphone. Figure out how much space you have left for a battery, then get one custom made. In contrast, the Tesla Model 3 uses the new 2170 cell, which will be the battery that powers all future Tesla models and even their home energy storage solutions. Need more volts? Put cells together in series. Need higher capacity? Put those cells in parallel with other cells. In this way, Tesla can absolutely mass produce these cells and configure them based on car. This flexibility is why Tesla can offer a wide variety of range options. By adding more cell blocks in parallel, they can increase range without changing the core voltage of the system. Tesla has a goal of producing batteries at less than $100 per kilowatt hour. This is very ambitious, and this small cell philosophy with the newly optimized 2170 cell is their recipe for success. The Gigafactory is Tesla's greatest asset because by investing so heavily into a vertical integration structure, they can control costs and production levels. In contrast, General Motors completely outsources the battery development to LG Chem, who produce and provide complete units ready to drop into their EVs. But if suddenly Honda and Toyota came with contracts to LG Chem, how would that impact GM? Vertical integration for battery manufacture is super costly, but does give Tesla a marked advantage over their competition. In fact, it might be their single biggest advantage. One question we often get is, who's actually making the battery, Panasonic or Tesla? The answer really is Panasonic. The Gigafactory is Tesla's vision for their own production facility pumping out their particular batteries, and they're able to house Panasonic personnel in a symbiotic relationship. It takes decades to master the chemistry of batteries, and that's where Panasonic comes in. The partnership is strong and benefiting both companies. We hope you've enjoyed part 1 of this 2-part series on the truth behind Tesla's Model 3 batteries. We wanted to break this up because the story of the raw materials is quite literally the most important aspect of the future EV story. Without stable and reliable supply chains, the Gigafactory would languish and Model 3 production would grind to a halt. We know we haven't answered the biggest question of how long Model 3 batteries will last. That comes in part 2 of this series. We really hope you'll subscribe and join the community and vote for future videos. We're Tuba Da Vinci. Thanks for watching.